Okay, so now that we've had a chance to look at some classification schemes for matter, let's move forward and talk about some of the states and properties of matter. The items we'll discuss here probably reach back to your elementary school days, and we'll stick with the relatively easy states of solids, liquids, and gases. There is that fourth state of matter, the plasma, that we won't touch on. It's a charged gas and it has special properties, but we'll stick with the classical solids, liquids, and gases for this chapter. Okay, so reviewing solids, again, I'm sure you've heard this before. It may have been a while, but I'm guessing at some point, or many points probably, you've heard these descriptions. So solids have a definite shape. That means that they don't just take the shape of whatever container they're in. They have a definite shape. Usually most materials are either crystalline, or there are a number of materials that are non-crystalline as solids, and they have a definite shape either way, but the non-crystalline materials, amorphous materials we call them, they have no regular repeat pattern within their solid shape, but they do have a definite shape. They also have a definite volume, and again, to go back to that idea, the particles are close together in a very rigid pattern, and they vibrate slowly in their fixed positions. So what about small things, powders, flour, for instance? So many of us have flour in a container on our kitchen shelf, and it seems to take the shape of the container. Again, that's because the flour or small sand granules or salt or sugar, these things are small crystals that have a definite shape themselves, but because they're so small at the macro scale, they'll take the shape of whatever container we put them in. But again, if you were able to have a really tiny container that's the size of one of those grains of sand or salt or sugar, that it's not going to change shape in that container size. Now moving to liquids, liquids have a definite volume but not a definite shape. So these truly do take the shape of their container, and therefore, if we pour water into a glass like we see in the slide, it'll appear to take the shape of that glass container. If we were to pour it into a graduating cylinder that's tall and skinny, it would look higher at the same volume, but again, it would be the same overall volume. It would just take the shape of the tall, skinny container. So whatever container the liquid is in, it truly does conform to that container shape, unlike the solids that we just mentioned. Even if they're really small and they seem to take the shape of the container they're in, if we had a small enough container, the solids are rigid, whereas the liquids flow. Okay, and that has to do with the particles being close together, just like in solids, but they're not fixed in a crystal lattice. For instance, for crystalline solids, the particles are able to flow around each other, and they move very slowly in random directions, and that's what allows for this flow of liquids. Okay, so sticking with that idea of flow, we move into gases, which have neither definite shape nor definite volume. Again, if we get down to the size of atoms, then yeah, if we had an atom-sized container, the volume of the gas would start to matter. But for the world we interact with, what we call the macro scale world, the gases have effectively no definite volume, no definite shape. They take the same shape and volume as their container. So if you were to pour a gas into a 2-liter bottle and cap it, now the gas has occupied that full 2-liter bottle. If you were able to pour that gas into now, say, a 1-liter container, and cap it, it would take the shape and the size of that 1-liter container. The reason for gases being able to behave so differently from solids and liquids is that their particles are much, much further apart. And the little graphic there with the balloons and the blown up image of the atoms, that's even far too close together for gas atoms most of the time, unless we're talking really high pressure, really low temperature. For the most part, the gases are very far from one another, and they don't really even interact much aside from an occasional collision with each other. But the gases are composed of fast-moving particles that have little attraction to each other. So they're moving so fast, even when they collide, they don't have much time to interact. Whether they collide with another gas molecule or the sides of the container, the gas particles are sort of like hard billiard balls. They hit and then they recoil, and they do interact very, very briefly, and it's not a totally inelastic collision, but it's a very, very small magnitude compared to the intermolecular forces in a solid or a liquid. And we'll have much more in-depth exploration of gases later on. Okay, so if we want to summarize things, Table 2.3 in your text does a nice job of summarizing solid, liquid, and gas by talking about shape and volume, arrangement of particles, interaction between particles, movement of particles, and then some examples of some common solids, liquids, and gases at room temperature and pressure. So that's a nice review. It pretty much just says what we talked about, so I won't go into any more detail there, but certainly take some time to look at it if you're having trouble in your mind keeping the concept solid, liquid, and gas straight. Okay, so now it seems like a good time to pause and have a learning check. So identify each of the following as S for solid, L for liquid, or G for gas. So A, it has a definite volume but takes the shape of the container. B, its particles are moving very rapidly. C, it fills the volume of the container. D, it has particles in a fixed arrangement. And E, it has particles that are close together and are mobile. So go ahead, if you haven't already identified those, jot it down, pause the video if you need to, and we'll take a look to see how you did on the learning check. Okay, so taking a look here, A, definite volume but takes the shape of the container, that's a liquid, right? Gases would have no definite volume, a solid would have definite volume and definite shape. So liquid's the best answer there. For letter B, its particles are moving very rapidly. That's G, a gas. Solids and liquids, they're moving, but not nearly as rapidly as in the gas phase. C, it fills the container. It fills the volume of a container. That's also G, gas, right? A liquid would take the shape, but it has its own volume, as a solid also has its own fixed volume. D, it has particles in a fixed arrangement. That would be S, solid, because you have ordinarily for crystalline solids you have a solid a crystal lattice with very fixed arrangement, just some vibrations but not a lot of movement within the lattice. And then E, it has particles that are close together and are mobile. Well, the close together could be solid or liquid, but the fact that these are mobile particles, they can flow around each other, means that it must be L, a liquid. So hopefully that went well for you. If not, again, try additional problems, homework problems, and chapter problems. If you're still stuck on these solid, liquid, gas properties, please get in touch and I'll see what I can do. Okay, so if we're thinking about physical properties of matter, whether we're talking solid, liquid, or gas state of matter, the physical properties are observed or measured without affecting the identity of a substance. Again, if it affects the identity of a substance, changes the identity of that material, then it would be a chemical property. If we consider common ones, common physical properties would be shape, physical state, which we just talked about, solid, liquid, gas, changes between those states, boiling and freezing points in particular. We're just changing, say with a boiling point, we're changing from the liquid into the gas, and therefore we're now taking on the volume of the container, whereas in the liquid state we were having our own fixed volume, and we can easily go back and forth. That doesn't change the identity of the material. Freezing and boiling points just talk about when the phase changes happen. Density is a physical property of a given material, and then color of that particular substance is unique usually to that material. Okay, so the fact that we've got, say, a gold color for the element gold, or copper color for the copper metal, that's very different than a lot of silvery looking metals, which is what most of the rest of the metals look like. So again, colors can be the same for different substances, but color is a physical property of a given substance. Alright, so if we consider the element copper, some key physical properties of copper, it has that characteristic copper color, an orangey red color to the metal. It's odorless, you can't smell copper. Melting point is very high, 1083 degrees Celsius. Boiling point even higher, so 2567 degrees Celsius. At 25 degrees Celsius, obviously it's a solid if it doesn't melt until over 1000 degrees Celsius. luster. It's a very shiny metal as opposed to, say, dull things like a lot of powders have a dull appearance to them, typically more characteristic of non-metals than metals like copper. Conduction of electricity, conduction of heat, again, being a metal, copper would have excellent. And even for metals, copper is one of the best, which is why copper is commonly used in electrical wiring, why copper is commonly used in say copper pipes for baseboard heating in homes. So all those physical properties of copper, again, we're sticking with copper metal, we're not changing it into another chemical substance, but those are some key physical properties of the copper itself. Okay, so if the physical properties were things like appearance, whether it's shiny or dull, what color it is, what physical state it's in, those are all considered physical properties. A physical change occurs in a substance if there is a change in physical state. So a change in state being solid to liquid, liquid to gas, gas to solid, or solid directly to gas. All those things are possible. A change in the physical shape. If we take that copper pipe that we talked about for, say, baseboard heating, and we cut it up into smaller pieces, that's a physical change. It didn't change the identity of the copper, but it did change its physical appearance. So no change in the identity, no change in the composition. It needs to stay copper metal. It just is a change in either being solid copper metal or bringing it up to the melting point and making liquid copper metal, or all the way to the boiling point and making copper metal as a gas. So again, a physical change does not change the composition or identity of the substance. So looking here at water, water is a very unique substance in the universe, but it's a very common substance here on Earth. So we tend to think about water as very boring and mundane, but actually water is very special, and as far as we know, life can't exist without water. Also interesting on Earth is that water is found in all three physical states, solid, liquid, and gas, right? So the physical change that water undergoes when cycling between those different states, it doesn't change the water molecule. It changes the arrangement. In ice, for instance, the water molecules are in that beautiful crystal lattice from the forms of ice that occur naturally anyway. Those crystals have a hexagonal arrangement that actually makes them less dense than liquid water, and that's one of the reasons water floats. Solid water, ice, floats on top of liquid water. That's very important for aquatic life in regions like ours, where we do tend to get freezing over of small lakes or rivers during the winter time. If we think about the liquid water again is very important for us. It's the form we as humans tend to take in for drinking. And then obviously we do a lot of cooking with water, so we would bring water to its boiling point for things like cooking spaghetti or other dried pastas, for instance. So is heat added or released when liquid water freezes? Well, if we think about the processes going from a solid to a liquid to a gas, all of that takes energy to break up those interactions. The interactions are strongest in the solid, and then they're still quite strong in the liquid. And finally, there's almost no interaction between particles in the gas phase. So it takes energy to break up those interactions, and again, increasing amounts of energy as we go from solid to liquid to gas. Therefore, as we reverse, as the gas condenses or the liquid freezes, we actually release some heat. So when water changes from a solid to a liquid, that requires the input of heat energy. From a liquid to a gas requires the input of heat energy. But when the gas condenses or the liquid freezes, those actually release some energy. Likewise, you could go directly from solid to gas, and that would require energy, and then finally going directly from gas to solid would release energy. And if you're ever in a situation where, I don't know, you're a spy or something, some James Bond type scenario where you're someone far more important than me, and you have the choice of being dropped into boiling water or being killed by steam, pick the boiling water, because the steam actually has more energy, and as the steam condenses, it will release energy, and then it's of course at the boiling point of water anyways. So that's why steam burns, if you're going into the health profession, steam burns are usually much more severe than burns with liquid water, or even boiling water. Alright, so focusing in on those changes of state. Melting and freezing. Of course, melting and freezing are the same temperature. The melting point and the freezing point are the same temperature. It's just a different idea of where we're starting and where we're going in terms of physical state. So at the melting point, a solid is converted into a liquid, and that's also sometimes called fusion. At the freezing point, a liquid is converted to a solid. So right at either of those temperatures, you're likely to have both the solid and the liquid present. And then as you go above the melting point, you're likely to have mostly liquid present and the solid is essentially gone. Below the freezing point, you're likely to have solid present and the liquid essentially gone. So two names for the same temperature, just considering which direction you're going. If we're thinking now about the liquid going to the gas or the gas going back to the liquid, we don't usually talk about that in two different terms. Usually we just refer to that as the boiling point, which technically is the liquid going to the gas. We don't have a condensation point that we commonly talk about, but obviously that would occur at the same temperature for the same substance. And since it takes energy, actually a lot of energy, for the liquid to go to the gas phase, it gives off a lot of energy when the gas goes back to the liquid phase. We don't commonly think about this unless, of course, you're in that James Bond scenario we mentioned a few slides ago, where your arch nemesis has captured you and offers you the option of boiling water or steam, and we said we'd take the boiling water. Or hopefully you'll never find yourself in the situation where you have a steam burn, but that's another place where you would notice that very significant condensation energy, the heat released as the gas condenses. One way that scientists represent this idea of temperature increase and how it affects the movement of particles, the relative position of particles, the physical state of particles, is with what we call a heating curve. So that's showing what happens as we add heat to a substance, and the heat added is typically your x-axis. We see what happens to the temperature of that substance along the y-axis. So if you have a horizontal line, that's where a phase change is occurring, whereas in contrast, a diagonal line shows that that increased heat is going to increase the temperature of the substance. So if we start at the far left on the x-axis, we're at a solid below its melting point. And so as we add heat, that solid, the particles in the solid vibrate more and more until they finally get to the melting point. And so notice at the melting point, there's a time where we're adding heat, but no temperature change is occurring. All of that heat is going into taking the particles in that lattice and breaking them apart, allowing them to flow around each other. And that takes a little while to get that much heat energy into the solid to completely convert it into a liquid. So by the end of the melting horizontal line, now we have essentially all liquid. So as we add additional heat, the liquid temperature goes up because the movement of the particles increases, and that's what temperature is, a measure of average kinetic energy. Eventually we hit the boiling point. Now notice it takes a significant amount of additional heat added to get that liquid fully converted to the gas. And then finally, obviously, once we hit that point, any additional heat energy goes into making it a gas, and then making the gas increase in temperature. And ultimately we could make a plasma if we were going to talk about plasmas in this course. So notice how much more significant that boiling horizontal line is compared with the melting horizontal line. And that's why if you had that gas at the boiling point versus the liquid at the boiling point, there's all that additional energy that would be released. Obviously, as we talked about steam burns, that's why steam burns are so significant. Boiling water burns are no fun, but steam burns are even more dangerous and even more damaging because of all the additional heat energy that's released by that gas condensing back to the liquid phase. Okay, so the heating curve was going in the direction where we're adding heat to the substance, and that heat is being used first to increase the motion of the particles and then to change phase. A cooling curve would be the opposite. If we look at the cooling curve, now at the extreme left of the x-axis, we start off, in this case, as steam above the boiling point of water, and then we condense and finally become all liquid water, and then that liquid water has the heat removed, causes that liquid water to slow in its molecular motions, and then finally at the freezing point to convert into the solid, which has very fixed position and very little motion, and ultimately we could go down all the way to absolute zero, or as close to it as we can achieve, and we would remain frozen ice. So additional heat removed just goes into slowing the vibrations until, if we were to achieve absolute zero, we'd have essentially no molecular vibrations at that temperature. Okay, so it's the same idea. The diagonals, now they're going down because heat's being removed. So those correspond to just change in the average kinetic energy of the particles within a given phase or state. And the horizontals are now the opposite of what they were before, because the heat's being removed for the condensation and the freezing temperatures. So melting and freezing and boiling and condensation, those are probably terms you've heard many, many times. Here, this slide addresses a couple terms that may be new, or at least relatively newer to your vocabulary. Sublimation and deposition. Sublimation is the process that describes the physical change of a solid directly to a gas, and deposition is the process that describes the physical change of a gas directly to a solid. So these don't always occur, at least not at the temperature and pressure we tend to observe in the time that we're on the Earth, the winter, summer, spring, and fall. Usually most materials that we explore during those times are able to make the normal transitions. But there are a few substances, dry ice being one important example of a substance that does sublime and deposit at room temperature and pressure. So one of the reasons dry ice is used for refrigeration is that you don't have a whole bunch of liquid to clean up at the end, right? Dry ice is nice and cold. You can get it in blocks, and it's very good for keeping materials refrigerated. And then at the end, any liquid you see, which does happen, there is small amounts of liquid, that's water vapor that's condensed into liquid water. That's not the carbon dioxide, which is the component of dry ice. The carbon dioxide doesn't liquefy at room temperature and pressure. The carbon dioxide goes directly from the solid to the gas. And then the way that we make dry ice is by taking that gaseous carbon dioxide and converting it directly to the solid. So carbon dioxide is a great example of a substance that both sublimes, goes directly from the solid to the gas, and deposits, goes directly from the gas to the solid at the conditions where we cool it at ordinary pressure, okay, or warm it at ordinary pressure in the case of the dry ice melting, actually subliming, not melting, right? Dry ice doesn't melt, regular ice melts. And so we have, again, a nice table that gives some examples of some physical changes and different things like changes of state. We just talked about dry ice, which doesn't go through the liquid phase at room temperature and pressure, but certainly at different temperatures and pressures you can get liquid carbon dioxide. So it just depends on what conditions you're going through. For change in appearance, again, making a solution or boiling off the solvent in a solution would be examples of physical changes. You can dissolve the sugar rather in the water. You can get the sugar back by boiling off the water, which you could also collect after you condense it back to a liquid. Changing of the shape, so hammering a gold ingot into shiny gold leaf, or drawing copper into thin wire. That's a couple examples of changing of shape, and then changing of size, cutting into tiny pieces or grinding into smaller particles. So we didn't change the chemical makeup, we didn't change the composition, the physical layout of the substances. In these cases, we didn't change what they're made of, I guess, is the take-home message. They're still the same physical substance, they just have a different physical appearance. Of course, this is a chemistry course, so chemical properties and chemical change are probably pretty important to what we do, but we couldn't understand the distinction if we didn't talk about physical properties and physical changes as well. Chemical properties describe the ability of a substance to change into a new substance. So whereas a physical property couldn't give us a new substance, a physical property talks about how one substance changes into another. During a chemical change, you take a certain substance and you form a new substance, and that new substance therefore has a new composition and new chemical and physical properties most of the time. So that's why if you get a color change, or if you get heat given off in a chemical reaction, these are because there's a difference in what you've made at the end versus what you start with at the beginning. So one example of a chemical change would be iron nails react with oxygen in the air to form rust. So the iron itself is a metallic, shiny, silvery metallic solid. It reacts with oxygen, a colorless, odorless gas, and it forms the reddish, brownish iron 3 oxide, Fe2O3. So you take two elements in this case and you make a compound. You don't have to be making elements into compounds or compounds into elements. That just happens to be the case here. But what you do have to do is you have to take one or more unique physical substances and then chemically combine them to get a new substance. Here we see table 2.6 from our text, which gives a nice listing of some chemical changes. So if we look at the tarnishing of silver, that's why people have to polish their silver from time to time, because the silver does react with oxygen or sulfur compounds to give that black grainy coating. Burning of wood, that's an important one for anyone who's using wood pellet stoves or some form, even just burning wood logs in a fireplace to heat their home. That's burning of wood, obviously, and that's quite a bit of interesting chemistry going on. Making caramel, caramelizing sugar, is actually a very complex process that we don't even fully understand. And if anyone's tried to do it, it's actually a lot tougher than it sounds. So there's a lot to it to get that sugar caramelized correctly. And finally, we already talked about the formation of rust. Every metal rusts to some extent, but when we say rust, we tend to be talking about iron becoming that red-orange iron oxide rust. And then we see in table 2.7, we have a summary of some physical and chemical properties and changes. So a physical property, as we said, it's a characteristic of a substance. Then we gave a bunch of examples. For a chemical property, it's a characteristic that indicates how a substance reacts with another. So paper can burn, we have iron can rust, silver can tarnish. We have a lot of organic liquids are flammable. They will burst into flames if they're given a spark or a match lighting, or even just reaching their temperature. So those are all examples of physical or chemical properties. Physical or chemical change, again, a change in physical property that retains the identity of the substance, that's a physical change. A change in which the original substance is converted to one or more new substances, that's a chemical change. So it's really key difference. A physical property or a physical change describes a given substance and changes it undergoes where it retains its identity as a substance, whereas chemical properties or chemical changes have to deal with how one or more substance reacts to form one or more new substances. Alright, so it seems like a good time as we're wrapping this chapter together to take a moment for a learning check. So in this learning check, we're going to classify each of the following as 1, physical change, or 2, chemical change. So A, burning a candle, B, ice melting on the street, C, toasting a marshmallow, D, cutting a pizza, and E, polishing a silver bowl. So go ahead and put a 1 if you think that process describes as a physical change, or put a 2 if you think the process describes as a chemical change. Go ahead and pause the video now if you need to, otherwise we'll take a peek and see how you did. Okay, so there we have it. Burning a candle is indeed a chemical change. That wax is becoming carbon dioxide and water, and among other things. B, we've got the ice melting on the street. That's just a physical change. The solid water is becoming now liquid water again. C, toasting a marshmallow. That involves caramelizing some of those sugars. That's why we get that nice color change. And if you're not careful, if you're like me and you put it too close there to the flame, you end up with charring and making actually elemental carbon. D, cutting a pizza. That's a physical change. We're just taking that whole pizza, which is a substance, and we're cutting it into smaller pieces. They're all still the same substance. And then finally, E, polishing a silver bowl. Well, we talked about silver and tarnish. and that the silver polish is a chemical reaction to take away that tarnish. So that's a chemical change too. So if you missed any of those and still don't understand why, still aren't quite sure about the difference between a physical change or a chemical change, or a physical property and a chemical property, please do try some additional problems. There's some great end of chapter problems. There's 1 or 2 in the homework set as well that you can look at. And if you're still having trouble, of course, reach out to me and I will try my best to help you make those distinctions. Alright, so this wraps up our discussion of states and properties of matter.